So we'll kind of pick up where we left off. We started thinking about the last topic that we're going to talk about with multiple linear regression, right? So this was going to be joint hypothesis testing. So if we're looking through any of those materials that we had for the exam. So I said last class, the steps that I would go through is that formula sheet, fill that out, make sure I know what every formula represents. I'll then start working through these practice exams and try to figure out if I could provide support as to why the correct answer is what it is, right? Not simply just take it as though it's like another exam. So any question you see here should be something we already covered with the exception of joint hypothesis testing today. So we'll kind of finish that up and then we'll just start going back through and reviewing either some of these problems or just some additional examples of the types of questions that you'll see on the exam. So I'll talk a little bit more about the exam when we kind of get to that portion of the class, but for now, we're going to finish up that last kind of topic. So what we're looking at here, new file that we were looking at last class was that MLR week 7. So we were quite a bit further down here. I've got some additional things I might show you, but before we get there, we want to look at, if I have it, maybe I added more than I thought. Here we go. It's all the way down here. So we're going to start looking at kind of this class 2 work. I'll kind of pick up with this example when we jump to Stata. So we're all the way down here in like line 240. Okay. So when we started adding in these independent variables, this is kind of a reminder. We said, what's definitely going to go up as I add more variables to a regression? R squared. R squared has to go up. In fact, we had an example last class where it went up to like the 5th decimal, but we could prove even then it went up. So it might just not display as though it's increasing, but at some decimal, we know that it's going to have to be increasing. Okay. So the next thing that we're going to think about is we have to add in one variable at a time. Well, when we look at the statistical significance of one variable, we just simply looked at its what? Whether or not that variable had a statistically significant relationship, we looked at the coefficient estimate and the p-value associated with that. If the p-value was less than alpha, we could reject this assumed true value for that coefficient, which was we always assume it's equal to 0. Well, what if I add in multiple variables at the same time? So let's say I have this original naive regression model, which is I'm just trying to predict y with one x variable. Well, I know that's probably going to have a pretty low R squared because there's probably more than one thing that is going to be influencing what the value of that y variable is. So I add in additional variables, x2 and x3, but I want to know is adding them at the same time, does it have joint significance? Now, what could this also be a solution to that we talked about last class? Not quite a solution, but if I have two variables that I think are what? So if I have two variables that are something and I include them at the same time, our standard errors of at least one variable will be influenced, possibly both.
Multicollinear.
Imperfect multicollinearity, right? So if I think I might have that issue, maybe I say, well, I know that if I look at the individual significance of these variables, it's going to be screwed up. But what if I add them at the same time, right? Does it provide joint significance? And we might just want to do this even if the variables aren't imperfectly multicollinear. We might just want to do this in general. So what if I want to test at the same time? Did adding both of these variables in, was there no effect? Or was the coefficient estimate for both of them not equal to 0 on their own, but simultaneously equal to 0 when I add them into my model at the same time? So this is what we're going to call joint significance. Is that coefficient on each variable simultaneously equal to 0 when I include it into my regression? So this joint hypothesis test, right? What we're really looking for is, right, why couldn't we just simply look at each one? Well, think about it this way. We kind of going back, talking about almost like reviews type stuff. If I have when I'm looking at my p-value, right, I could kind of go back and think about that was the probability that I rejected the null, even though I shouldn't be, or what we call our type 1 error. You don't really use it a lot in this class or, kind of go back and mention it, but that's always what that p-value is representing to us, that even though we're rejecting that null that the coefficient is equal to 0, we could be wrong. Now, we're only going to be wrong probability of the time of whatever the p-value is. So that's why we wanted the p-value to be relatively low. And then we know we're not making these errors. Now, the problem is, if I think about that p-value represents the type 1 error for each variable. So kind of the probability my test statistic falls outside of this range. Well, for both of them, that would actually be 0.5 times 0.5, right? That would be the probability I'm making simultaneous type 1 errors, right? So the probability I'm making a type 1 error for both statistics, right, would actually be even lower. So it's not really our desired type 1 error. When I was comparing to these critical values, they were associated with 0.05, 0.01, and 0.1. And it's easy to think if I have two variables, it's just the type 1 error times, but what if I have 4 or 5? Well, now it's getting even further away from that desired type 1 error. So, right, how can I kind of solve this problem, right? So we're going to have to rely on a different distribution. I've mentioned this a little bit last class, but when I add variables, we said we know the R squared has to go up. So am I ever going to see when I add variables that my R squared goes down? No. So I'm only really looking at one side of the distribution. I know that I'm always going to find that R squared, the difference is positive, that it went up. However, even though I saw it go up by, let's say, like 0.01, is that statistically significant? It could just be that I had a skewed random, like had a sample that showed me that, but there's a distribution, just like we have a distribution for every individual coefficient. Right? We could think about it as, excuse me. So we know that true value of whatever that coefficient is, our estimate should be centered around that. But sometimes I might see an estimate's a little bit higher, sometimes a little bit lower, etc. We're now thinking about with the F distribution, it's going to have a longer right tail. So this, we were always using our student T, or what I'll give you on the exam, and I kind of bring this in on Tuesday to show you what it'll look like. Anytime we're looking at that student T, we said as long as the sample size is over 30, we could use what to approximate it. Started out with it a long time ago. Before we looked at the student T, we talked about the standard normal, right? And as that sample size gets higher and higher, our student T looks more and more like that standard normal, so we can use those values to approximate. Not going to be the case with the F distribution, right? Doesn't matter if we have a higher sample size or, you know, it's because it's a completely different distribution. It has this longer right tail. So really what we're looking at here is going to be the estimate for that difference between our R squared from what we're going to call the restricted model and the unrestricted model. The unrestricted model is the model that we added more variables into. The restricted model was the original one that left them out. So we know this difference will always be positive. So it should be centered around whatever that true difference is. But when we actually see this, we don't really write it this way, but just to kind of connect it with what we were talking about with slope coefficients, we're really only seeing estimates of those R squareds. Now, if you actually look at notationally, I'm not supposed to write these as hats. I'm supposed to write them as bars, but it doesn't really matter. It's just notation, right? So I know that the difference will be centered around whatever the true difference is, but I might happen to see a value that's a little bit higher than that or a little bit lower than that. Right? Excuse me. Now, what we're going to assume this difference is, if I want to know, are these jointly significant? I want to know, did it increase my R squared? What do you think I'm going to assume the difference actually is? 0, right? And then any evidence I see, I'm going to convert into not a test statistic from the student T distribution, but a test statistic from the F distribution. So we would just call that an F statistic, right? It's still a test statistic for what that difference is. It's just coming from the F distribution. So we're going to assume that that increase was 0. Did we see evidence that supports it actually did increase? Now we know that the estimate we come up with will be positive, but how far away from 0 is it? We'll measure that with the area to the right of our test statistic, which now we don't need to multiply it by 2. The area to the right simply would represent our p-value. Okay? And now it goes back to exactly what we were doing before. Is the p-value less than alpha? If it is, I can reject that change in the R squared was 0 or nothing. I can actually say that there was a statistically significant increase in the amount of that Y variable I could explain, or a statistically significant increase in that R squared value. Okay? So that's at its core what we're doing here. Okay? The more practical side of this, right? So we've got a one-tailed test. We already kind of talked about this. Is how would I calculate that F statistic, right? Well, we're gonna have Stata do this a lot for us, right? But we want to know that if we had some output from Stata, we could actually calculate this by hand. I might ask you to do that on a question on the exam. So all I'm gonna do is look at what was and here I kind of changed notation to read a little bit better. But I have kind of, what was my restricted kind of model's sum of squared residuals, or what was it not explaining, minus what was my unrestricted model not explaining. Now, when I write it this way, it gets a little confusing because you're probably like, well, wait, weren't we looking at the difference in the R squareds? Well, if the R squared is the proportion I can explain, 1 minus that was the proportion that we couldn't explain. So what's happening to the amount of variation that we can't explain when I look at the unrestricted model? Well, if the R squared is higher, the amount I can't explain is always going to be lower. So this statistic will always be positive. The restricted model will always be able to explain less, which inherently means kind of whatever's left over, we're going to have more. Right? So this is kind of our residual sum of squares, or what we're not explaining.
That'd be always negative then.
No, right? So the restricted model has like one variable in it. So its R squared will be higher, right? The proportion, sorry, its R squared will be lower. It can't explain as much of the variation. But if it explains less variation, right? How much is left unexplained? A higher amount.
Oh yeah, sorry. So
We're looking at the residual, what it can't explain now, which is why this kind of statistic does get confusing, right? Because when we're simply thinking about it as the difference in the R squared, we would actually know the R squared for the unrestricted model has to be higher, which means that the amount that the unrestricted model can't explain will always be lower, making this a positive statistic.
given to us in the regression output right on the top part with the total.
Yeah, we'll take a look at it here in a second, right? So this is for right now, just the equation. We'll see where we can get this from Statham. Now, Q here, right? I think I've got it. Please set up for us here. There we go. Is going to be the number of restrictions that we have. So the number of restrictions, it's kind of weird to think about it, but it's the number of variables that we're adding into the model. The thing about it, it's restrictions. It's how many of the naive regression left out. Okay? And then n minus k minus 1, right? This is just going to be our sample size. K, just like we had with the adjusted R squared, is going to represent the number of total variables in that unrestricted model. And then minus 1's minus 1, right? And kind of our base group, we're going to use, or kind of what we're kind of taking the proportion of, is what was the amount left unexplained from that unrestricted model. So it's not the most intuitive ratio here, but you can kind of see what it factors in is how many restrictions do we have? Because we know if I add in more variables, what's always going to happen to my R squared? It's always going to go up. So that difference will always be larger. So what do? We divide by the number of restrictions so that as I add in more things, it's going to cause my F statistic to actually be lower, closer to 0. Less likely I can reject the null. Same kind of idea as we had with all these other things. This is like a consistent theme. The sample size is higher. What happened to this fraction? So if I have a larger denominator, the fraction is going to go down. If my denominator for my F statistic is now lower, what's going to happen to my F statistic? It will now be higher. If I have a higher F statistic, which is just a test statistic, my p-value, or the area to the right, is getting lower, making it more or less likely I can reject the null. P-value is lower, I should be more likely. It's going to be less likely that it's it's going to be more likely that it's less than alpha, right? So we can kind of, if it helps, this is how maybe I would do it. If I've got that formula sheet in front of me, I could do the same thing we did at last class with like our individual coefficients. If I've got my F statistic, here maybe it's easier to see it this way. So this is like my number of restrictions. And then I've got SSR here over n minus k minus 1. If I take a higher sample size, what did that do to this fraction? It made it lower. If this denominator is lower, what happens to my F statistic? It gets higher. If my F statistic is higher, what happens to the area to the right of it? It goes down, which that area to the right, I don't even have to multiply it by 2 now. That represents my p-value. If my p-value is now lower, is it less likely or more likely it's going to be less than alpha? More likely. So I'm not even asking you how much more, how much less. We're just thinking about the directional changes here is as far as I would ask you to run a question. So with everything, we're looking at the joint significance, looking at our kind of changes to our just squared, changes to the statistical significance of an individual coefficient. Higher sample sizes always made it more likely we can reject the null. We don't even, I mean, you want to memorize that, that's fine. But thinking through this, though, that way I can do a change in either direction, increase or decrease in N or sample size, and for whatever statistic I'm looking at. And you'll have those equations in front of you. So I would suggest doing something like this with the arrows. Prevents you from making like an intuitive mistake trying to just think through this in your head. Okay? Any questions on this idea? Okay. So what does this kind of look like? Now I'll mention this. We're not going to use this in like anything we do. But there is, and I put a link up to the F table. That number of restrictions that was in our kind of denominator of the numerator, and then n minus k minus 1, which was like the denominator in our denominator. Those are what we're going to call degrees of freedom. And they actually, the F distribution isn't one distribution. Just like technically the student T, every single sample size had a different student T distribution that was a slightly kind of wider. Same thing applies to the F distribution, but now we have an even wider set because it depends both on my sample size and the number of variables I included, but also my number of restrictions. So there's like this huge table where you can find the degrees of freedom, find the corresponding critical values. For us, I'm not going to make you actually find them using that F table. We're just going to rely on that p-value, because no matter what F distribution we're using, the p-value decision is always, is our p-value less than alpha? So that's really all we have to focus on when we're interpreting these results we see from Stata. Okay. Any questions? So this is kind of a complete slide. If you're going back and want to use this for something in another class or a project, I won't make you use these degrees of freedoms or ask you questions on. All right, so a little bit of a side. We're now going to go back and think about, did these two added variables have joint significance? We're going to start out assuming they didn't, that they're simultaneously equal to 0. Okay? If we can reject the null, what we're saying is that by adding these, they had simultaneous significance. If we fail to reject, we're saying they didn't change our model's predictions or didn't change the amount of variation our model could explain for that Y variable at all if we fail to reject. So if we think they matter, we essentially want to be able to reject, okay? So I kind of mentioned here's another, here is our F statistic. You can actually calculate it in a slightly different way. This one might be a little more intuitive, kind of to the question earlier. I'm really at my core looking for, was there a difference in that unrestricted and restricted R squared, right? So I can rewrite these things because if I know this is the proportion that they explain, this represents somewhat the proportion they can't explain, we could use either one of these. So I think when I actually look at the Stata output, I'll use the R squared for us. It makes it a little bit easier. Okay? So let's say I have this example. And I run the regression, and I've got age, GPA, and a dummy variable for female. So I look at this, I'm like, all right, everything looks great. All of these variables highly statistically significant, right? P-values are all less than 0.01, so I can reject at all levels, right? Now, I could grab my restricted R squared. So this is the model. I'm going to leave some variables out. And this was like my naive regression where I left some of these variables out. So here was like my starting R squared, or my restricted model's R squared. I then go to my second regression, which, and notice here, what was I doing? I won't ask like a coding question like this, but just to kind of start to touch on some issues that we'll see pop up. Why did I add the robust command in here? What must I have thought about one of the variables? That the errors of GPA in college, in your first year of college, they must have been what? Heteroscedastic, right? So I didn't want to treat them as homoscedastic because I know if I did, that would actually make my standard errors to what? Well, heteroscedastic, I said a way to think about this is that there's more variation in my errors, right? So if I don't treat it as heteroscedastic when in fact it is, the errors I see are going to be too low, which if my standard errors are too low, once again, I'm trying to do a little bit of review here as we cover this last topic. But if I go back to just thinking about individual significance, that was our coefficient divided by our standard error was our test statistic. if I treat it as homoscedastic when it is heteroscedastic, we said our standard errors will be too low, which means my test statistic will be too high, right? Which means the area to the right of my test statistic, which represents half my p-value, so I have to multiply by 2, but that means my p-value is going to be too low. If my p-value is too low, am I more or less likely to reject the null? Which that means I'm more likely to be rejecting it when in fact I shouldn't have been. Right? I was treating those errors as homoscedastic. The standard errors actually should be higher, lowering the test statistic, increasing my p-value. I should actually be less likely to be able to reject the null if I correctly treat them as heteroscedastic. Now, I don't have to worry about that here because I added in that robust command. Now I'm treating them as heteroscedastic. So I then went out and was, okay, there's this like math science, the number of math science credits you're taking. If I'm just like, before I look at these, the more math and science courses you're taking, what would you expect the sign of that coefficient to be on your first year college GPA?
Negative.
Yeah, right. Those are usually harder classes. And so we expect the more credits you're taking from math and science, oh, sure enough, it decreases your predicted GPA by what? About 0.05 points. Now, when I'm making these interpretations on the exam, and this is where the exam, this class has been comprehensive. Everything we've done, I mean, we started out even with the review talking about test statistics, p-values. We're using it also, even like simple linear regression questions. I can ask you them from a multiple linear regression. So you're probably going to see this exam looks like we're covering just what we've talked about the last 2 or 3 weeks. But really what we talked about the last 2 or 3 weeks is using everything we talked about in the first 3 weeks, right? Critical values, confidence intervals, p-values, statistical significance. Even when I'm interpreting coefficients, we interpret them the same way from simple linear to multiple linear regression, but there's one change. When I interpret this as every additional math science credit I took lowered my GPA by 0.05, what else do I need to add into my interpretation? Why were we adding in additional variables? Because now I have the same interpretation, but I can say holding all else constant. So holding constant the student's age, high school GPA, gender, and whether or not they were working. Then if one of them takes an additional science math credit, their GPA would go down by 0.0. That's a lot more powerful of a statement than just saying if I take one additional, because if I didn't include these controls, we likely have omitted variable bias, right? And it's a lot more powerful. I can say holding all these other factors constant. What are, you guys in other econ courses right now? What's a Latin term that you use in there a lot?
Ceteris paribus.
That means that, right? That's all we're doing. We're doing the statistical side of economics where we're trying to hold everything else constant, ceteris paribus, by including them in our regression, okay? So don't forget when you're interpreting something from a multiple linear regression, part of your interpretation needs to be, you haven't turned in your problem set yet, it's not due, so you can always update this. Or if you're thinking about the exam, you always need to add into your interpretation for these slope coefficients from a multiple linear regression, holding all else constant. It's a powerful statement, right? So we added in 2 additional variables simultaneously. So our Q, or the number of restrictions we have from our initial model to this one, would be what? 2. We've added in 2 variables simultaneously. We want to test to see, did they have a statistically significant impact on our R squared, or the proportion of the variation our model can explain. So we've got Q is equal to 2. I now have my unrestricted models R squared. Right, so that's part of what I was going to need in my F statistic equation. So I've got R squared from the restricted, R squared from the unrestricted, the number of restrictions Q I have. What would my N be? Got what? 1401. That's just my sample size, number of observations. The only other thing in that equation that we didn't have was K, which was the number of total variables in my unrestricted model. So how many variables do I have in my unrestricted model here? I count them, 1, 2, 3, 4, 5. In fact, I've got a typo here that I copy and pasted. Right? You can also always look at how many coefficient estimates you have. That's the number of variables that you have. Right? So we go back. Where is it? There it is. We've got our unrestricted R squared, we've got our restricted R squared, we've got Q and K. I could actually calculate my F statistic by hand, okay? So if I wanted to do that, right, let's take that equation, plug all those values in we just found, and I get an F statistic of about 3.57. Now, it's harder to think about using the F statistic and comparing to critical values because I said every single like combination of the number of restrictions and sample size, different F distribution. So I'm not going to ask you questions about calculating the test statistic and then determining statistical significance. I might ask you a question where you have to look at this equation from output, identify your R squared from the unrestricted and restricted model, identify Q, identify K, and calculate it. If I ever ask you to make a statistically significant decision, I'll give you the p-value, or you'll be able to find it from the output. So here I can think about, did this have, well, if I looked at Stata, I end up with a p-value associated with this of 0.0259. So at what levels can I say that adding these two variables in had joint significance? Can I say it at the 90% level? So my p-value less than 0.1? Yes, so I can reject at the not, so with 10% significance, I can say, yes, these added variables did explain more of the variation in, now I already forgot what the Y, first year college GPA. Could I say at the 95% confidence level or 5% significance? P-value is less than 0.05, so yes. Can I say at the 99% confidence level or 1% significance? Not quite. My p-value is not less than 0.01. So statistical significance, it's the same kind of process we were using for our other test statistics. Okay? Now, the command that we run in Stata is very easy. Once I run my unrestricted model that had the added variables, after it, I just run test and the variables I want to test for joint significance of. It's as easy as it is in Stata. That will give me my F statistic, which we could calculate by hand. It will also give me it looks in the table for us and tells us, it identifies what F distribution I should be using and tells me what that p-value should be, okay? So hopefully, if I give you this output from this joint significance test, this should be not a hard one on the exam to determine statistical significance. I understand that calculating the F statistic might be a little bit harder of a question. And we'll kind of look at this. I've got some additional examples as well when we go back and look at this in Stata. So this is just kind of additional work. This is just going to be some review. So let's go ahead, open up Stata, open up that last do file we're looking at, scroll all the way down to where it says class 2 work. And I've got some regressions. We'll start to think about multiple things that we've talked about, definitely touch on joint significance, but I might add in some additional things for review that we want to think about for the exam. Okay? So I had this data set laying around, and I think it was called this powerlifting in class data file. So I had some old powerlifting data that I found at one point. You don't have to know anything about powerlifting. I'll explain any of the variables to you here. But I thought it was kind of interesting because it gave us just a different setting. Also, some of the variables kind of line up nicely with some of the topics we've talked about. So I'm going to generate this variable, which if you're not, have no idea about powerlifting at all, basically there's different divisions where they can use like devices that allow them to lift more weights. So that's all I'm doing is identifying here whether or not it was one of these divisions where they can use these like crazy elastic suits and all this different stuff, right? So just a control I might want to use later on. Now, the original naive regression I'm going to run is here is the total kilograms of weight lifted in these powerlifting meets, and here was the individual's body weight. What do you think the sign of that coefficient is? So how would I interpret the coefficient on that variable? A 1 unit change in my X variable, so 1 kilogram heavier of an individual, the coefficient will be the predicted change in the total kilograms they could lift. Larger people, I would probably expect, can lift more weight, right? So I'm probably thinking this is positive. I'll run this regression. Sure enough, it is. Right? Now, how would I interpret the constant here? So this is where the interpretation of our constant can get weird, right? So what would the interpretation of my intercept or constant be here? So it's the predicted value of my Y variable, what equal to 0? The X variable. So someone who weighs 0 pounds, their predicted weight lifted is 77 kilograms. That doesn't really make any sense, but we have to remember at our core, what are we doing with multiple linear regression and simple linear regression? I'm just looking, so if I had like body weight in kilograms, and here I had kind of total weight lifted, most of the data, nobody weighs like under, I don't even know, right? Like, I don't know what the smallest person would be, but probably not a lot of people less than 100 kilograms in that data. I mean, there's generally larger individuals, right? I don't know. So most of our data is probably going to be up here. When we estimate these lines of best fit, we're estimating that relationship between X and Y, but it has to have a starting point, right? Even if there's no data points down here, that's still how we interpret what that intercept is. Okay? So your intercept does have weird interpretations sometimes. This is a good example of one. Okay? So the next thing we're going to do is say, okay, if I left out an important variable here, and this is where I could ask you to calculate the sign of the bias. This was kind of similar to problem set 2 has an example like this. You can look at the covariance between the omitted variable and the variable you included, the sign of the coefficient on the omitted variable, and actually calculate what the bias is. But more likely, and like I might ask you that question, but I'm also definitely going to ask you a question. So I'm telling you, this will be a question on the exam, where I ask you to put a sign to the bias. Okay. So if I have this example, right, and I think about, all right, let's go back and let's have this formula sheet pulled up since we're now doing some review, right? So I start to look through here. All right, I've got some equations here. Excuse me. Oh, did I not actually? Oh, here it is. So this equation, if I'm labeling it, is going to be the estimate that I see. It should be the true coefficient between these two variables, but also plus this bias component. So this is going to represent our omitted bias kind of formula that we need to use. So what does our bias depend on? What the sign of the excluded variable would have been if we included it, and the covariance between the excluded and the included variable. So let's think about this in the context of the example we have. And I was thinking about, what if I left out kind of this gender identifier, right? So if I have total weight lifted, and I run this naive regression, where I'm just looking at kind of the individual's body weight in kilograms, right? If I leave out this important omitted variable, of whether or not the individual is male, right? So if I run this regression, the estimate I'm going to see, here I'll try to color code this, will be whatever the true relationship should have been between body weight and total weight lifted. But it's also going to include a bias, and the bias would be from the fact that I excluded this important omitted variable of whether or not the individual is male. So the bias would be what that coefficient would have been if I did include it, times the covariance between that body weight variable, the variable I included, and the variable that I excluded. Okay? And then it gets divided by standard deviation of the variable I included. But for us, we're just trying to put a sign to this. So this, we'll see, won't matter here in a second. Okay? So if I want to think about, if I run this naive regression, what will the sign of this bias be? Well, if I did include male, I mean, I don't, this isn't true for any one or, two individuals, but if we take a biology class across most species, what is true about males relative to females? Generally, they have more muscle mass, right? They're larger, So the effect of being male, I might think about what impact would that have on total weight lifted? Probably positive, right? They have more testosterone, it's linked to muscle, right? It's not a biology class, and if you told me on the exam for whatever reason, maybe you think that men are like, overconfident so that they're attempting to lift more than they actually can. And so you'll actually see them lift less. Okay, just tell me why you think the sign is what it is, right? Now, what do you think the covariance is between being male, the omitted variable, and body weight? Well, once again, in general, males tend to be taller and larger. So I think that's probably positive as well. Standard deviations are always positive. Variances, standard deviations are also, the sign of my bias should be positive. The estimate that I see for my regression, if I run the naive regression, will actually be too high. If I include that omitted variable, I eliminate that bias, the estimate I see will actually be lower in this case. Okay. So if I omit this important variable, I can put a sign to that bias. Now, once again, if you had the story where you think men are overconfident and you thought this was negative, then the bias you would tell me should actually be what? Negative times a positive over positive. You would tell me there that the bias would actually be negative. Okay. So, you know, if I give you a question, I try to give you examples with variables that I think are obvious what that sign would be. But as long as you justify what you think that sign is, and I'm not going to grade you on the justification, I'm just grading, you know, I'm just telling me what to believe those signs of those statistics are, I would grade it accordingly, right? So if we go back to our example, when I run this regression, I think that the coefficient I'm seeing is too high. It has a positive bias built in. If I instead include this male variable, if I think that that bias was positive, once I include it and I eliminate that, my new estimate should be lower. So I'm going to go ahead and run that. Sure enough, it went from 5 to 3. Once I control for whether or not the individual was male, because remember, multiple linear regression, this is the same interpretation. For every additional kilogram of body weight, this is the predicted increase in total weight lifted. But now it's holding constant the gender of the individual. Any questions over anything there?
It's kind of just a question about the tests based on seeing that problem. So since we're doing like the multiple choice one, it is multiple choice and it's like probably going to be at home. Are all of those questions going to be like completely no need for any interpretation at all? Because
well, yeah, if I give you a question that's multiple choice, I can't have it be open to interpretation, right? So that's going to be a lot more of like calculation based ones where I'm giving you values. So on like a multiple choice one here, I might give you this output. I leave out the naive regression, right? And maybe I tell you, I'll explain this in a second. So maybe I give you just this output here. In fact, this might look very similar to a question that's on the exam, not like these specific variables. But if I give you the variable that, or sorry, the regression that includes the omitted variable, I then give you this covariance matrix, right? If I then asked you, if you run the naive regression, what estimate will you see? Well, or what would the sign of the bias be that you see? Is probably more what I would phrase it as. Well, I have that regression with the included variable, so I can go ahead and grab beta 2, right? The coefficient on that omitted variable. The other thing I need is the covariance of the, if I did run the naive regression, that omitted variable and the variable I included, so I can go to that output. I've got my covariance right here. The only other thing I need is the variance of the variable I included in the naive regression. So our naive regression, we had just body weight. Like I hadn't, let's say I didn't like, I wouldn't show you this, right? So that you're okay. So here's the variance of body weight. Now I have everything I need to plug in to figure out what the size of that bias would be. That's not open interpretation, right? So yes, to your point, if it is a multiple choice question, I obviously can't have it structured as like, give me the sign. Is that what you're getting at? Yep. Any other questions on that? Okay. I got in time. Okay. So let's look at some joint significance stuff here. So let's say I had this regression and I'm looking now, I've got body weight, identifier for male, age, and kind of this kind of identifier of a, did I even See if I specified this on my, no, I did. So this was like without any assistive devices. It was just a dummy variable for if they could not use any assistive devices, right? So if I'm thinking about, go back here, it must have, let me make sure that I'm doing this what I thought. So with male, my R squared, 6437. So I was just running the original naive one. Just to kind of, I added some of this in, so I want to make sure that this is clear. So if I run kind of my initial naive regression, I've got this R squared of 0.43. Oh, that must not have been what I wanted. What did I want here? No, I did want this regression. Hold on. So we should, oh, it's because I, so what's my R squared here? 0.6437. All right, 0.6437, okay? So this was like my restricted model. I was leaving out some variables, right? So I went and I grabbed that R squared. So that's my R squared from the restricted model. If I then run the unrestricted model where I included age and this raw identifier, kind of dummy variable, I run that, getting what, 0.6827. So I know why these numbers didn't match up because I wrote this and realized if I gave you guys the full data set, it was too large. So I had to restrict the sample. So these numbers were a little bit different because I had to restrict the sample. So we then are kind of changing these, and this kind of helps us see how we would calculate that F statistic. So if I gave you the restricted and then the unrestricted model, and I ask what's the joint significance of adding in these two additional variables? So I can grab my restricted R squared from that one that only had the two variables. I can grab the unrestricted R squared from the one that included all four. That's kind of what I've identified here. If I then want to calculate my F statistic, we had the unrestricted R squared minus the restricted R squared. So I've now got those two values. What was our Q? That was our number of restrictions. So the number of variables I've got different between the restricted and unrestricted model would be what? 2. So I've got Q as 2 here. Now down here I had 1 minus the unrestricted R squared. So it said our unrestricted R squared was 0.6827 here. Line up with this, here we go. So we need to change these. So it's what? 827 and then 457. So this would be like if you were working through a different problem, you're just changing the values to be the restricted, unrestricted R squared. Here, this was our unrestricted R squared. So that was 0.6827. Now, this is where, when I wrote this, I had to give you a smaller sample size. I forgot for class. Instead of 86,000 observations, I've only got, what, 10,000 here. So this value would be our sample size. Here, I don't want kind of K being 2, right? I want the number of restrictions that are in my unrestricted model. So here that would be 4. And then basically, if I want to have this display, right, I could create a new variable, or showed you last class, I can have Stata do math for me by simply taking this here and running it after the display command. So it gives me an F statistic of about 614, right? Pretty large, right? Assuming I've got my, assuming I change that sample size, right? So that's how I would kind of plug my values in from Stata output into that test statistic or F statistic equation to come up with what my actual F statistic is. Right? Now I could create a new variable and then summarize it. That was just a different way of doing it there. But ultimately I have like this really large F statistic. Notice when I did it with a larger sample size, even if I had the exact same restricted and unrestricted R squared, or if they were similar, what should having that higher sample size do? we said in every statistic we're looking at, higher sample sizes will always make it more likely we can reject or increase our test statistics. When I had the full sample of 86,000, similar restricted and unrestricted R squareds, notice what happened to my S statistic. It wasn't whatever I said there, 614, it was 5,000, right? So this kind of helps to show higher sample sizes will always increase those test statistics. If I increase my test statistic, my p-value is getting smaller, making it more likely I could reject the null. Okay. Now, this is still a really large test statistic. I'm guessing if we run that test command, so I said the way we do this, and I don't think there isn't this in the problem set, but like if you wanted to in the future, if I want to run these joint hypothesis tests, all I do is after I run the regression, put in what the variables I want to do the joint hypothesis test for is. I go ahead and run this. So it's giving me that 614 F statistic still, and the p-value is basically 0. Okay. So at what levels can I reject that these added variables had simultaneous and no significance? I can reject at all levels. Okay. Now let me see if I have something in here. I don't think I do. Let's try something here. I don't think I put another data set in here. I didn't. So let's do H squared and I'll try including, well, I know it's going to be significant, but we'll see if this works. If not, I'll kind of try to make the point using a different data set here real quick. Yeah, it's not. So let's go back. So before I kind of move on, so that's how we can kind of calculate an F statistic. We can look at the output, determine whether or not they had statistically joint significance. Some of this stuff at the end is kind of similar to what I already worked through, which was an example of not just how to put a sign to the bias, but how you could actually come up with what the size is, right, by plugging it into that equation. I wanted to make this point. So let's go up to use it in a data set that we had last class. So one of these free ones, where was it? Here it is. Use this BQ smoking data set. Button it like this. So I need to clear out whatever I've got in current memory. So let's say I run this regression. Let me think here what's going to make sense. So I want to look at cigarette use, cigarette price, income, age, education, restaurants, and just keep it at that. Okay. So I'm going to run this regression, kind of think about this output. Let's give me something that I think I can use. Yes. Okay. So I've got these 5 variables, right, which I included. So I can start to think about the interpretation here of any one of these coefficients. So this would be like, what if I had education? Well, let's do income. How would I interpret my income coefficient here? For every 1 unit change in X, so for every additional $1 of income, the predicted number of cigarettes smoked, and I think this was packs, goes up by 0.0001, right? This might be counterintuitive. So this actually means that people with more money are predicted to smoke more, holding constant everything else in this regression. Okay. So I'm going to run a joint hypothesis test on 2 variables. So this is like my unrestricted model. And I'm going to say, okay, what if I did this joint hypothesis test and I did it for age and cigarette price? Now, this seems odd, and I'm hoping this works out in my favor. I'm just guessing here to kind of prove something. So hopefully it lines up. This is not always a fail, like this isn't always a guarantee. But what's the most surprising result if you're looking at the statistical significance of these variables? Is the price of a pack of cigarettes statistically significant on cigarette use? Not even close. So this is kind of weird, but holding constant income, holding constant all these other things, the price actually doesn't look like it's an influence at all on how much someone is smoking. Now, that's because what is likely, right, my cigarette use associated with income, but I'm holding that constant.
Is restaurant their employment?
So restaurant, I think when we used this before, I mentioned this was an old data set, if you could smoke in restaurants or not in the state or in the county. So it's just a dummy variable. Which once again, that kind of goes against what you would think. If you can smoke in restaurants, people are actually less likely to smoke more here, which is kind of counterintuitive. But I want to make this point to like the broader econ like principle. If cigarette prices don't have a negative coefficient here, well, they're not statistically significant. So I would actually say that the effect of the cigarette price, I can't say it's any different than 0. In fact, if I didn't give you the p-value or the test statistic or the standard error, might be something I do on the exam. Wink, wink. So a whole bunch of heads just snap. Not doing this for the sake of me, right? The things I'm telling you in class here today are, I have the exam written, so I likely know what's going to be on it, right? If I left these things out, why would you tell me that cigarette price is not statistically significant at least one level? What else could you use other than the test statistic and the p-value?
The confidence interval.
My confidence interval, right? All I was doing with the confidence interval, we said any value in my confidence interval, if I run a hypothesis test, I should be failing to reject that as a possibly true value. What value is in this confidence interval? 0. So can I reject it? No. Any confidence interval that includes 0, we would fail to reject the null that coefficient is equal to 0. Okay? Same thing here. If that 95% level, look at education. Would I reject based off that p-value? 0.03 would be less than 0.05. So yes. So 0 should not be in my confidence interval. Is it? Nope. Right? Just barely outside of it. Right? So I can use those confidence intervals to determine. Now I can only show you one confidence interval in this output. So I can't ask you about all 3, but you can use those confidence intervals as well. Okay? Might be something I do. So getting back to my econ kind of principle, if it looks like the effect of price on quantity is 0, what would I say consumers are here? Very, well, price is changing. They keep buying the same amount. They are very inelastic. We can actually estimate elasticities from data. Now we'll look at this more after the exam. We're actually gonna need this isn't quite right because I actually need like percent changes. So we're going to talk about how we can get data to be percent changes after the exam with some different types of nonlinear regressions. Okay, but kind of at least in mentioning it here. So I'm going to then run this joint hypothesis test for age and cigarette price. Okay. Did I call it the wrong thing? Yep, I forgot a P. So let's run that joint. Okay. Now ahead of this running this, I had a feeling, because the other one, the p-value is basically 0. I had a feeling this would probably not provide me with enough evidence to reject the null. So this is where they're not exactly the same thing, but they're closely related. Why did I choose, if I wanted an example where there was no joint significance, right? The p-value is way greater than our alphas. Why do you think, based off of these results, I chose age and cigarette price? What's true about those 2 variables? If I was to run a individual statistical significance for each of them, could I reject at any of our conventional levels? Well, the p-values are 0.12 and 0.96, so no. So my mindset, if I run a joint significant, it probably is going to be that they're not jointly significant either. Now, that's not always a 1-to-1. These are some extreme examples. So let's say instead I looked at age and, I don't know, something that was individually significant, like education, right? So education had that 0.03. Well, age is not on its own statistically significant. Education on its own is only significant at what, the 90 and 95% levels. If I run the joint significance test for those two, I actually get that jointly, they do have some statistical significance. So it, it's not always a guarantee that if I have both of them be individually significant, that I would also have joint significance, right? It doesn't necessarily have to be the case. In this second example, I had one variable that was individually significant, one that wasn't, but jointly, I still find that they had some statistical significance. Okay. But just trying to show you that like this p-value doesn't always have to be as low as 0, right? Now, the reason why my other data set was because we had really large. What always is going to make us more likely to reject the null or have small p-values? Very large sample sizes, right? Okay. I guess we've got what, 15 minutes? Let's go back. I'll ask you guys, are there any questions that you have or any types of things that are kind of, I don't know, causing you any confusion, or you'd want to see me talk through an example? Or
when you did the robust on the regression, would you like us to do that function for every random regression, or should we just do it when you tell us to check?
So on the exam, you're not going to be, so I'll make this kind of clear talking about the exam, right? And I've tried to, but when I give you like, you look at these practice exam, I'm not ever asking you to give me specific code. I'm showing it to you, right? So you need to know how to kind of interpret at least like the results from a specific code, but I'm never going to ask you like, what is the code in Stata for doing X, Y, or Z, right? In practice, what is good to do? If I control for heteroscedasticity in my error term, even if it's minimal, I'm at least controlling for it. So if you looked at like academic papers, what do you think they always choose to do? Robust standard errors or correct for heteroscedasticity. Because I mean, there's almost no guarantee that they're exactly homoscedastic. They might be, right? We have tests to see if they are or not. But even if we do run that test, we know that we're going to be making type 1 errors some of the time. So in practice, like you always probably want to use robust standard errors, right? Now, when it comes to like the problem sets, unless I'm specifically asking you to run it, you don't need to include it. Right? But in like the real world, right? Any regression output you see, they're likely going to have robust standard errors, right? Like unless I'm specifically asking you for like from here on out, you don't need to run robust standard errors. Nope. Any other questions or anything? Since we're kind of getting closer to the end, at 15 minutes, anything related to the exam or material that you're kind of interested in? So I'll do what I think, since I'm getting some kind of, yeah.
Go over interpretations, the interpretation questions, so like interpret V1.
The coefficients. Yeah, so let's look at this practice exam. Let's say I have this one. Right? So here I've got I think I tell you what these variables represent in the problem. So like, this will look similar to the exam, but it's kind of a running like here, income is in thousands. You've got, unemployment. I guess here, I have to go back up. Unemployment is the percent, and then red county is a 1 if they had a larger portion vote for Donald Trump, right? Or the Republican candidate from this old kind of voting data. So if I've got a dependent variable that's a 1, 0, anytime I interpret my coefficients, it's a change in that X variable. So let's look at unemployment. This was measured by percentages. If the unemployment rate goes up by 1 unit, that would be if the unemployment rate goes up by 1%, right? That's how I was told it was measured. And it is going to decrease my Y variable by 0.04. What are the units of my Y variable if it's a dummy variable? Decreases in the probability. Right? So it would be a decrease in the probability that that county voted red or for the Republican candidate, right? Holding everything else in my regression constant. So holding constant the income of the county, the pop, or whether or not what was production. I think it was probably if like it had a just the percent of the jobs that were in this production or factory work in the county. So holding those two things constant, if the unemployment rate went up by 1 unit or 1%, the change in my Y variable, since it's a 1-0 variable, it'd be a decrease in the probability that county voted red. So here, that's as simple as our interpretations are gonna be. It's always a 1-unit change in X, the impact that it has on Y, holding everything else constant. Now, the kind of key is if I have a dependent variable, what are my units? My units are gonna be changes in the probability. If I had a different regression, so here I had like the violent crime rate, and now I have a dummy variable on whether medical marijuana was legalized, how would I interpret this? Well, if I have a dummy variable on the right-hand side, a 1-unit change would be going from the 0 to the 1 group. So a state that had medical marijuana legalized, it would predict the violent crime rate actually goes up by 35, right? And this is like 35 per 1,000 people, or however the variable, whatever the unit of the variable I'm told is. Now, what's probably true about this regression? I'm guessing there might be some questions, and maybe I didn't even ask them here. But like, if I only run a naive regression like this, what do I probably have in that coefficient estimate? I don't have any other variables. Do you think there's other important omitted variables here that might be correlated with both legalizing medical marijuana and the violent crimes in that state or county? I would guess probably yes, right? There's probably a story I could tell about why that bias is too high, where there's a positive bias, or maybe even why it's too low, right? Kind of depending on what omitted variables I have. Okay? But that's how we would, you want to think about being able to make interpretations for these different combinations, right? So I want to have well, I'm the dummy that can't spell dummy. All right, so if I have a dummy variable for my dependent variable, and I have a continuous variable as my independent variable, or I could have dummy variable and a dummy variable. I could have continuous, or I could have continuous dummy, right? So throughout all those practice problems, or if you're going back to the old quiz questions, or you're even going back looking through the problem set. So I posted the second problem set solutions. You start to kind of go through those. You're going to have some type of example of every one of these throughout all of those questions. So know how to kind of make interpretations from any 1-4 of these combinations of dummy variables, either as my dependent or independent variables, and then continuous variables as well. And then the added thing I would say is when I start to have multiple linear regression, the interpretations with these combinations will be exactly the same. But when I have multiple linear regression, what's the added thing I need to put into my interpretation? Holding all else constant, or everything else in the regression constant. So I've got something that I think, given where we're at on time, on Tuesday's class, I can pick and choose some of these, but I think it's probably going to be a lot more efficient for you guys, and it's a review class, so I can kind of guarantee I'm not going to use an in-class quiz. I want you to be here and ask the questions that you have, so that's the most effective for you to improve your performance on the final, or on the final, well, on the final too, but on the midterm, right? So try, if you can, before Tuesday's class, to at least, even if you can't work through all these problems, start to look through them and identify which problems you think, just on the face of them, even before, what you kind of are going to have the biggest issue with, because that's what I want to spend the most time on. Right? So you'll kind of notice if you go back to these beginning ones, some of this is like some basic mean relative to the median. So we might talk about some skew. We're talking about like individual test statistics, what the relationship is with a p-value to a critical value. So some of that review stuff, there might be a couple questions like that in the exam, but then very quickly it's going to jump to simple linear regression. Now, we were still using, like I said, all of that review stuff we were using in our simple linear regression and our multiple linear regression, but the bulk of the exam is going to come from when we started like covering simple linear regression. And so around like week I came back, basically. It's like 4, 5, 6, and 7. Now, 1, 2, and 3, like I said, they're still popping up there because we need to be able to, know what statistical significance is, p-values less than alpha, confidence intervals, right? We talked about today. But I would say if I'm studying, kind of mainly focus on what we've done with regression. In addition to that, scroll down here. This is due at the end of the day. So you're here in class. I want to reward that. You don't have to do it right now. In fact, if you want to take some time to do it, I would suggest not. There's no time limit on this. But if you complete this and answer all the questions, I've got it set to be 3 points. The exam is going to be, so I think what I've decided on, unless I get some answers I'm not expecting on this, I am going to give you a take-home portion, which will be on Canvas, which will be timed, but it'll be like 45 minutes to 60 minutes. I'm kind of deciding exactly how much time I might take 1 or 2 questions off of what I currently have prepared. I'm kind of still working on getting the point totals to be exactly what I want. I've got the set of questions. I'm just trying to figure out where the points are. So it'll be about 10, 11 questions, right? That you'll have quite a bit of time to work on. And I can't limit the use of your notes, right? So in my world, I think this is something attractive if I was a student, because it seems like I'm more likely to get those questions right if I have more time per question and I have my resources available to me, as opposed to like putting them all on the exam, but just taking off like having fewer questions. So this should be a way, this take home portion will be a good way to, I think, to help improve your overall grade, right? The in-class portion of the exam will be open-ended, right? So I say multiple choice on that take home. There'll be a few where it's like calculation based. But once again, you'll have your notes that you can use, like you've got more time per question. So I'm thinking that it's going to make those questions a lot easier for you. Now, the open-ended ones in class, you generally have like an example where there's 3, 4, 5 questions associated with like one kind of state output or one example. That way, like you're not restarting on every single question. It's like the same variables, but just different questions about that same output. So that there will be 6 questions that you would have in class, each one having on average, like 3 or 4 parts, right? Somewhere in between there, right? But that way you're not like restarting. Even those questions, some of them are like similar dependent variables. I'm just kind of changing things around just a little bit, right? So you have slightly different results from 1 to 2 to 3 to 4 to 5 to 6. Based off of what I've done in the past, that generally is better for grades than if I make all of the exam in class, because you have a little bit less time per question if I do it that way. So this pre-exam assessment has some questions. And if you answer all of them, I'll take this 3 points that you get from answering it by the end of the day, and I will simply add it to your midterm score. Okay. So the midterm is going to be out of 100 points total. You're going to get 3 points added in. You complete this. Seems like a pretty good deal to me. Okay. So here is kind of a weird one. I don't use this type of question on exams and things, but it's more of a survey based. I've got different kind of categories of topics. I want you to read through them. And this is where I say you don't have to do this right now if you want to. Hopefully, for y'all, has anyone tried to open this up? You've got it. Yeah. So you basically will order these based off of what you think is going to be the most difficult on top down to the least difficult, right? So you just rearrange these, and then I'm going to look at that. That helps me know on Tuesday, if people are shy, maybe what I should focus on a little bit more, right? Or even if I get questions about certain topics, maybe I'll spend a little more time on them if it lines up with what the majority of people who filled this out are saying they kind of are finding the most difficult, okay? Now, this is kind of some more actually just interested in the data. Now, I'll never show anybody your individual data. And in fact, I'm not going to look at individual, like as you had individual responses here. I'm just going to look at the responses as a whole to the class. So don't lie to me. I can somewhat figure this out based off of your in-class quizzes and just kind of whether or not I see you here. But I am interested in the actual data side of this. And I might use this to run some regressions that I show you after the exam, right? Which is how many class periods have you not attended or have you missed, right? I think we'll be shocked to see what that correlation is with exam performance, but maybe I'm wrong, okay? And then also, what do you expect? So I want to try to gauge how accurate you're feeling about your performance on the exam prior to taking it. So if you had to, right now, based off of when we cover material, assume the mean is 75, what kind of grade category do you feel like you're going to get going into the exam? That kind of helps me see people who are thinking they understand the material. Does that correlate with performance as well? So these are all statistics that help me write better exams, also kind of identify where there might be some issues existing, and also whether or not I'm kind of making people too confident or, not confident enough, right? We'll skip this one for a second. The last one is going to be, what do you prefer? So this is kind of this combination. That take-home exam where you're going to have more time per question, right? Overall, you're going to have your class portion, but then a portion that, it's like for the next, until we meet into the next class period. So you're going to have about what, 4-ish days, however you want to kind of count that, to complete that take-home portion, or have it all in class where you have less time per question. You have no notes or resources available to ask to answer any of those questions, other than the formula sheet. Kind of which one would you prefer? Right? If this is wildly everybody wants this one, maybe I'll change the mind of what we're doing for the in-class exam. Once again, I imagine this is going to be what most people prefer. And I'm not just making this decision just off this, but I want to kind of get some feedback from you guys to kind of see what your thoughts are. And then kind of 4, if you had to, without like a preset list, what concept have you found the most difficult that we've covered in this first half of class? Right? So this can be as narrow or as wide of a concept that as you want. This is like open-ended. I'm just trying to kind of get an idea about what people are finding to be the most difficult, so that kind of moving forward. And even if this isn't a specific topic, this portion doesn't have to be related to like the exam. This could be the problem sets, right? Maybe you're just having difficulty using the program stated in and of itself, right? Maybe you're having difficulty kind of learning the coding side of it, and that's what you have found most difficult. So this doesn't have to be just related to the exam. This can be anything in the course that you have found to be most difficult up to this point. And once again, if this is even a way in which that I'm going through things in class, if you'd want to see me spend more time in Stata, less time through the theoretical side of things, that could be a response as well. So I'm always trying to get better, but it's hard to get better without feedback and also without data from you guys. So this is like my goal of these pre-assessments with the exam. So this I've got open till the end of the day today. Not only should this help me out, it's going to help you out for the second half of the course, right? Help me adjust things to try to match how you guys are learning or what you are finding difficult. And then also, you get done by the end of the day, it's 3 extra points you get added to your exam. Okay. So you'll see an announcement post up about this for people who aren't here, but I'm kind of making you guys aware of it right now so that you see it up there, you know exactly what it is. Okay. So please, any questions to class on Tuesday. I am literally going to show up with no agenda. My agenda is to answer the questions that you guys have. And I might have some things back pocket that if I'm shy, I'll go to. I'd like to kind of have as many questions as possible during that time. Okay. So fun, safe fall break, and I will see you guys on Tuesday.